All right, in part B of this example, we're looking at this basis, or not basis, this set given x squared minus 1 and x squared plus 1. But we're in P3, okay, which is all polynomials with real coefficients of degree 3 or less. Okay, and so clearly this is going to be some subspace of P3, but we want to show that first it's linearly independent within this schema and then extend it to P3. As we've discussed, you know that first of all, you don't have enough vectors for this to even span the space of P3, so it's clearly not a basis yet. And so the dimension of it is not, and that's assuming that these two are linearly independent. Okay. All right. So let's first find out about the linearly independence, and then see if we can extend this to the entire set of P3 to form a basis for this set. Okay. All right. So similar to part A, first let's write out x squared minus 1 and x squared plus 1. So let's put these into a form that is congruent to the set or the basis set of P3. So the standard basis for P3 is you have well, before I write that out, polynomials of degree 3 usually have something of the form a constant term plus something times x plus something times x squared plus something times x to the third. Okay, so usually there's something of this form, and so we usually say that the basis set, or the standard basis for this, is of the form, and I'll put in the coefficient 1 even though that's redundant, just to kind of give you that sense of where it's coming from. So 1 is the identity for the real numbers, and then each of these is an individual set, and so the combination of these are like this is like I, j, k, and some other unit vector in Rn. So this is a polynomial space, and each one of these is the unit vector, if you will, in that space, corresponding to the polynomial vector. And so these are the coordinates then of a standard of the standard basis for P3. Okay, so let's write this basis that we have in terms of this set. Okay, and so if we do that, clearly this is going to be -1 plus, well, we don't have any x terms, so we're going to call that 0 plus x plus, looks like we have 1x squared plus 0x to the third. Okay, and then likewise, this one we have a +1 plus 0x plus 1x squared plus another 0x cubed. Okay, and then just like we did in the previous example, using the exact same theorem, we can express these as columns in a vector, as vectors, row vectors, that we turn into column vectors of the same form. So we have what, 1, 0, 1, 0, and this one is also going to be, oh, this should be -1, sorry, -1, yeah, -1, 0, 1, 0, and this should be 1, put a comma in there, sorry, 1, 0, okay? So this is like my V1, and this is like my V2. Row reduction on it and see what we get out of it. Ah, so we have our two leading ones, or two pivots, as we were talking about previously. And so that shows that each of these vectors are linearly independent. So we can use these then to determine a basis for the set of polynomials of degree 3 or less with this set. So let's go ahead and create join the matrix here, M1. So M1, and then we're going to have the identity matrix added on to that as well. So inputting those all together, we're going to have, okay, and then where the first two columns will of course be the vectors from this set that we're interested in, and then the last 4 will be the identity. So if you could imagine drawing a line right here, this is the identity. It's a 4 by 4 because P3 has the constant, the linear, the square, and the cube term. So these are the identity matrix for that, and these are the two vectors with respect to the standard basis written out. Okay, so we're going to do the exact same thing. We're going to look at the row reduced echelon form of this matrix, M2. And we're looking for pivots or leading ones in the identity matrix, which shows here that our first one is in this location, and our second one is in the this location here. So it looks like our two necessary sets are going to be the x term and the x to the third term are the two matrices that we need to write out the final form. So to write out the basis set, I'll do that here. The basis set is going to be our initial one, x squared, the difference of squares here, squared minus 1, and then the sum of squares, x squared plus 1. Those were the two original ones. And because we have the second column in the identity component of the augmented matrix, identifying that, then our linear term is x, and our fourth column in the identity matrix, augmented identity matrix, shows that the I3 is also needed. So we need I think the x squared, the cube term is what we need for that vector. So there forms our basis. This is our new basis for P3. Okay, which is what we wanted to show. I hope that was helpful. See you in the next video.